Okay, so it's around 6:08. So let us wait for 2 minutes. Okay, so this is around 6 or 10. So I think we can start. Okay. Okay, so uh, let us start the fourth live session of the course entitled as Physics through Computational Thinking. And the instructor of the course is Professor Aditya Sharma. He's from Aizer Hotel. So uh, let us start. So in this tutorial or in this live session, so we will learn about a very important aspect of numerical calculations. So we will learn about derivative, integration, and how to solve a differential equation uh, by using Mathematica's inbuilt desolve function, and also by using this Euler method and all this. So we will learn about first derivative, derivative of a function. Then we will learn about how to integrate a function in Mathematica. Then we will learn how to solve a differential equation. So any general differential equation, so like this kind of form. So suppose this is a first order differential equation. So here will be a function of, it can be a function of both x and t. Like you have as equation of this kind, dxt equal to minus 2xt. So this is one first order differential equation, and using Mathematica's inbuilt function, we can obtain directly x as a function of time. We can get the functional form of x. So we will learn how to do that, and after that we will talk a bit about damped harmonic oscillators. So in this context, we will discuss about this LCR circuit. So previously we have discussed about LC circuit. So that is ideal harmonic oscillator. So in that case, there is no damping because there is no resistance, and due to no resistance, there will be no joule heating or energy dissipation. So that is an ideal harmonic oscillator. But in case of LCR circuit, like every circuit has practically everything should have resistance. So if there is resistance, there will be a joule heating, and this due to this joule heating there will be energy dissipation, and that dissipation can be characterized with the damping factor. So that we will talk about. And if we have time, or so we will talk about uh, this spring mass system a little. And after that we will have a general or about brief introduction. Solving differential equation using Euler method. So what is Euler method and how to do that? So we will learn about that. So this differential equation that in Mathematica we can solve them directly with the help of Mathematica's inbuilt command, or like in general case what we done in other programming languages like Mathematica, Python and all that. So we will solve this differential equation using this Euler method. So there are other methods also, RK2, Ranjakutta 2, Ranjakutta power 4, backward Euler method and all this. So we will go through in our next tutorial video. So in this video we will have a basic introduction about this Euler method. So let us proceed. So first, derivative. Let us learn and get familiarized with derivative, inbuilt derivative function of Mathematica. So suppose we have a function of x. So it can be of any kind, like, so assume of this kind, 5x square minus 2x plus 1. So we can do its derivative by hand. So the f of x dx, like the first order derivative. So that is uh, easy to calculate, 10x minus 2. And in that way we can go on higher orders. So second order derivative will be 10, and third order derivative, and the next all the orders they will be 0. So fourth order, fifth order, all they are 0. Now we for a simple function it is easy to evaluate, but if we have a complicated kind of function, so suppose we have a function of this, so let us denote this by g. So suppose we have a function of this kind, x cube plus log x divided by e to the power x square minus 5 plus, suppose 5 into log x. So if we have this kind of complicated function, and we want to, suppose we want to calculate its third order derivative. What- Hello, can you hear me? Okay, so so in this tutorial, first we will go through this derivative function. So what I am explaining. So basically, if we have a very simple function, and if we want to calculate derivative of that, so we can do that by in-hand calculation like this. So if we have this kind of simple function, then we can calculate its derivative easily. But if we have a complicated kind of function, like function of this kind, x cube plus log x by e to the power x square plus 5 log x. So and suppose we want to know its what is it, its third order derivative, then it is really cumbersome and tedious to do this by hand. So we can do this easily in with our Mathematica inbuilt function. So how to do that? So for that, so so this d command, so this basically represent a, Okay, so to compute derivative of a function, so suppose we have a function of this kind like 5x, and we want to calculate its derivative with respect to s. So for that we have to write down the following command. So if we do that, so it will give us derivative of first order. And now if we want to calculate derivative of second order, then we have to write down within third bracket what is the independent variable with which we want to take the derivative of this function, and what is the order of the derivative. So 2 means we want to calculate its second order derivative, and the second order derivative of this function should be 0. So you can verify that. So this is 0, and if we have here x squared, then it should be 10. Yeah. So in this way we can calculate derivative of any order. So let us try with another function. Suppose we have a cosine function, cosine of x, and we want to calculate its derivative. So suppose nth order derivative. So if we run that, so this is the derivative of this function of nth order. Now if we have we can have any kind of complicated function here. So let us write down a function 2x plus divided by. So this is our function 2x plus log x divided by e to the power x square plus 3 log x, and we want to calculate its third order derivative suppose. So for that we have to write down x comma 3. So if we calculate that, so this is our third order derivative. So this is a this is for function which has one independent variable. Now you can have function of two independent variable. So suppose you have a function of this kind, like, so now here is two independent variables. Suppose let us assume a simple function sine xy, and we want to calculate its we want to calculate this term del f dx dy. So we for that we have to write down this command in Mathematica. So d sine xy. So this is our function, and we want to calculate. So if we only write down x, then it will assume y as a constant function, uh, or just a symbol. So it will calculate its derivative with respect to x, and you can see that y is just a constant here. Similarly, you can calculate its derivative with respect to y also, and if you calculate with respect to y, then it will assume x as a constant function, and x will be outside. And you can do this derivative with both the quantity, like double derivative. So it will give us here. So in that way you can calculate derivative of any function. So function can have any number of independent variable. So this function have two independent variable, so it can have more than that, like 3, 4, 5, and you can calculate any order of derivative of any function. So with this d command, so this is basically our derivative. So what can be a use of the derivative? So we know that suppose we have a general function f of x, suppose ax square plus bx plus c. So what can be an application of this derivative function? So suppose we want to know where is the maxima or minima of this function. So we know that if a function uh, has a maxima or minima at a point, then its first derivative should be 0. That means if we calculate this term, tx 2ax plus b, this should be 0. So from that we can get the value of x where it can have minima or maxima. So it is so at this point this function can have minimum value or it has maximum value. So for that we have to check second order derivative of the function. So for that we have to check second order derivative, and if it is less than 0, then so suppose this is x naught, then this x naught is a maxima point, and if this is greater than 0, then this x naught is a minima point. So let us go through an example of this. So yeah, so suppose we have a function of this. So suppose we have our this function. So this is our function, and if we want to so first let us see how this function looks like. So for that we have to plot the function. So plot function of x, and with respect to x, so suppose plot from minus 5 to uh, let us see. Yeah, so this is how the function look like. So we can clearly see that around this point this function has a minimum value. So this is so a local minima. So in this region this is a minima point. So how to calculate how to get the point? So for that we have to write down the following command. So what is this doing? So this part, this d of f of x, this is calculating the derivative of this function of first order, and for minima point or maxima point, that has to be 0. So we are writing down this the derivative of the function uh, should be 0, and we want to solve this equation for to get the value of x. So if we run this, then we get 2 point where the first derivative is 0. So one is so let us simplify this. Yeah, so around minus 2.41. So around this point, here we have here the derivative of the function is 0, first order derivative, and around 0.41 the first order derivative of this function is 0. So now we want to know that what is the value of the second derivative at these points. So for that we have to write down the following command. So here we are calculating the second order derivative of the function. So if we run down this, so this is the second order derivative of the given function. Now we want to know the what is the value of this function at these points. Is it positive or is it negative? So for that we have to write down in the following way. So first we have to store this in. So let us store the value. So this solution, now this solution, it has stored the value of this x. So if we write down solution 1, so within two third brackets, so it will give the first element. So let us see. So it will give us the first element here, and if we write here 2, so it will give us the second element. And we want to check the value of this function at these points, at the first point of the solution and the second point of the solution. So let us check that. So we have to replace here. So what does this command signify? So we are basically evaluating this sec function. I mean, that means this function we are evaluating this function at the points of the solution. So if we do that, so it will, so this function have these values. So let us check for only for first point what will be the value. So if we, so it will give us, so this is the value of this function for this x value. And if we want to check what is the value of the function for the other x value, so we can write down 2 here. Yeah, so this is the second, for the second one. And if we want to see both at the same time, so we can write down only this. So let us simplify that. Yeah, so as we can, so we can see that this second order derivative value is negative and this second order derivative value is positive. So that means around this point it has a maxima, local maxima, as you can see that it is a local maxima. And around this point, this x equal to 0.41, and at x equal to 0.41, we are observing that the second order derivative value is positive. So that means around this point, this function has minimum value. So this is the use of this derivative function. So we can check where is the minima point or maxima point of any given function with the help of this inbuilt derivative function. So is there any question? So if not, then you can proceed. So this is about this derivative function. Now in the similar way, we can also integrate any function. So let us, so suppose we have any function of this kind like 2x, and we want to integrate the function with respect to x. So this integration, that we by hand we know how to do. So it will be x squared divided by 2 plus a constant factor. And how we so this is how we can evaluate this constant factor. So one way of doing this, so is to specify the limit. So suppose we have the limit specified a to b f of x dx, then we know that it will be half x square, and the limit will be from a to b, so it will be b square minus a square by 2. So this is the value of the integral. So this is called indefinite integral, and this is called definite integral. So with in Mathematica, we can we can calculate both the both type of integrals. We can calculate indefinite integral of any function, and we can also obviously specify the limit of the function. So let us see in Mathematica how to do that. So for integrate, we have to write down this kind this command. So for derivative, we have to write down d, and for integrate we have to write down this integrate. So and in the third bracket, first we have to specify the function. So this is our function. So let us take a simple function 2x. So this is our function, and we want to integrate with respect to which variable. So we want to integrate with respect to x. So we have to write down x here. So x. So if we run that, then it will give us the value of the integral. So there can be other variables also, so it can have more than one independent variable. So, so here it will only assume this t to be a constant value, and we can also integrate with with respect to more than one independent variable. That means we can also evaluate this kind of integrals. So suppose we have a function of two independent variables, and so this type of integral that also can be done with the help of mathematical. So where this type of integral is seen, so these are called basically surface integral, and this type of integral, so they are line integral. So surface integral we have, like we use in many cases, like suppose we have a circular disc and we want to calculate the area. So in that case we have to integrate with respect to both r and theta. So that is an example of surface integral. And so there are also volume integrals. So there we have three independent variable, three axes. So all this line integral, surface integral, and volume integral, that can be done in mathematical easily. So let us go through some examples. So this is a function of two independent variable, x and y, and we want to integrate it with respect to x and y both. So we are doing here surface integral. So if we run that, then it will give us the integrated value. And so in this way we can integrate any function, any kind of function, and we can do its surface integral, volume integral. So all that sorts of integration can be done with the help of mathematical. So these are basic things about this derivative, how to compute derivative of a function, how to integrate a function. So these are inbuilt command in Mathematica. So another thing, very powerful thing which you can do with the help of Mathematica is to solve this differential equation. So differential equations can be solved, like it can be solved in all the programming languages out there. So differential equation of this kind. So suppose we have a first order differential equation. Now to solve this, in other programming languages, you have to use some sort of algorithm like Euler algorithm or RK2, RK4. That we will discuss later. But there you have to do this numerically. But in Mathematica, with the help of command, so Mathematica is very powerful with symbolic calculations. So that is why there is inbuilt command to solve this kind of differential equation, and you can get the exact form, the functional form of x with respect to t. So if we have this kind of equation, suppose equal to minus 2x, so we can do this by hand. So what will be the solution? So it will be ln x to minus 2t plus c. So ultimately we can write x as a constant factor into e to the power minus 2t. So you can get this exactly this functional form in Mathematica with the help of Mathematica's inbuilt command. So what you have to do, you have to feed in the differential equation that we want to solve. So this is our given equation. It can be a, it can be more complicated. It can be more order, higher order. Like it can be a third order, fourth order. So like in case of damped harmonic oscillator, we have this second order differential equation. So gamma dx dt plus omega square x equal to 0. So you have to only fit this equation, and from Mathematica it will evaluate and give you the functional form of x as a function of t. So so let us see how we can do that. So first let me type here, and now let me explain what this is doing. So this dsolve we have, so this dsolve command is basically to solve the differential equation. And for any algebraic equations that does not involve these differential terms, that we can solve with the help of solve command. But if we in our equation, if there is differentiation like differential equation, then we have to write down this dsolve command. So what is the equation here? The equation here is y prime equal to minus 2y. So, or you can write down this as dy dx equal to minus 2y. So this is our given equation. Suppose we want to solve this. So uh, here in third bracket, we have write down the independent variable. So that means, so you have to specify which is the independent variable, like y depends on which function. So y is the dependent variable here, and x is the independent variable. And to solve a differential equation, so this is our differential equation. So in first order, you for to a first order differential equation, there will be one constant, and to evaluate this one constant, you have to give one initial condition or one condition. So suppose we are given x at t, we know this value at t equal to a, this is suppose a0. So if we know this, from this condition we can evaluate the value of a. So the general idea is that if we have an nth order differential equation, so for an nth order differential equation, we need to know n n initial condition. So in case of harmonic oscillator, so since harmonic oscillator is a second order differential equation, harmonic oscillator, second order. So for that, to fully get the functional form of x with respect to t, there we need two initial condition. So it can be position at initial time and this and velocity at initial time. So if we know these two value, from that we can calculate both our initial both our constants. So in the previous example, we have this solution. So suppose we know that x at t equal to 0 is 1. So if we know that, so we can put t equal to 0 here, and from that we will get a to be 1. So we if we know a, then we can fully write down x as a function of t. So this is e to the power minus 2t. So this is our initial condition. So in the dissolve command, first you have to write down your equation, and after a comma you have to write down your initial condition, and after that you have to specify what is your independent variable and what is your dependent variable. So if we omit x here, so it will give us error. So we have to specify this y, that it depends on x. So if we don't write x here, so it will give us error. So basically this dsolve command, it comes with three arguments. So first argument is basically the equation that you want to solve. The second argument is what is your dependent variable, uh, which variable you want to get the form, and the third argument will be what is your independent variable. So if we solve this, so this is our form of this. So you can see that we can exactly get the functional form of y as a function of x. So you can solve other equations also. So now suppose you want to see how this function, this e to the power minus 2x, it looks like. So for that you have to suppose you want to plot this. So for that, what you have to do, you have to write down this comment. So what is doing here? So first we are storing the 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 value, the functional form that we are getting in this variable ss. In ss we are storing this. Yeah. And so we have stored the value of this. And suppose and if we execute this, then this function. So we are defining a custom function here, and this function is a so for this function the independent variable is x. And and if so if we want to plot this, so what do you have to write down? We have to write down this command plot f x, and we have to specify the limit of x from 0 to 10, suppose. Yeah. So in this way we can so we can solve any differential equation and see how its solution looks like. So suppose you have any complicated kind of function. So let us write down a function. So suppose you have given a differential equation of this d2x dt square equal to minus equal to plus 2 dx dt plus uh, suppose t into x. So this is suppose your given equation, and you have two initial condition. So because this is a second order equation, you need to know two initial condition. So first one is suppose this x at t equal to 0 is 1, and x derivative prime or dx dt at t equal to 0 is 0. So this is your given initial condition. And suppose you are asked to show how this solution of how this x looks like as a function of t. So for that, what you have to do? So first you have to solve this equation with the help of these two initial condition, and you can easily get the functional form of x with respect to time. And once we get that, you with the command that I have just shown in Mathematica, you can get the how this x depend how x depends as a function of t. So it can be of any kind. So we will just see in a moment. So this kind of graph of any kind of function, you can see how the functional form looks like. So let us write down this function. So it is a second order differential equation. So write down here. So we have a double derivative. So this is our first term, and here we have 2 dx dt. So this will be first derivative, and you have another term which is, so let us just change the notation x as a function of t. So x at t equal to 0, x as a function of t, and independent variable is t. So you have to write down here t into x. So just write x t. So this is our equation which we want to solve. So answer. So this is, since this is second order differential equation, so there will be two initial condition. So this is one initial condition, and second one we can write down after a comma. So the second initial condition is x prime at t equal to 0 is 0. So this is our equation, and these are our two initial conditions, and we want to solve the equation for x. So x is our dependent variable, and t is our independent variable. So if we evaluate this, so just wait a minute. Yeah, so here should be double equal to. Just wait a minute. This one. Shoot. So it is just okay. So just let us check once how it is. I think we should clear first. Okay, so I think there is issue here. So you can see from here. So yeah, so here this is a second order equation. So this is typically a harmonic oscillator equation, that x double prime of double derivative equal to minus xt, and here we have two initial conditions, that x. So this is our first initial condition and this is our second initial condition, and after that we have to specify our independent, what is our dependent variable. Like so x, we want to know the functional form of x, so that is why we have write down here x, and this is our dependent variable, And when we are doing this nd solve, so nd solve is basically numerical solving. So for numerically solve this, we have to specify the range of t. So we are specifying that in this time range we want to solve, we want to know the how x is a function of time. So if we execute that and if we take the solution and plot this, then we can see that we can get the solution of this x. So we in this way we can do the solution of any kind of function, and we can get how the function look like as a function of time. So this is one example also. So we have here this equation, and we can see how the function look like. So there might be other. Yeah. So in this way, you can do the how you can solve any differential equation, any order. So this general kind of differential equation to n f of x t. So in Mathematica, with that commands, you can solve this equation. You can get x as a function of time, and you can plot that x as a function of time. Okay. So is there any question? Okay, so if not, then we will take a 5 minute break, and after that, we will go through this damped harmonic oscillator, this LCR circuit oscillators, and then we will have a brief introduction about this Euler integration method. So we will again resume after 5 minutes. Yeah. So can start. So in one of the previous videos, so we have learned about this a little bit about LC circuit. So in LC circuit, the equation, so we have an inductor, and across that we have an capacitor, and the equation that we get for LC circuit is D2Q D2 square plus 1 by LC into Q. So this is a equation of a ideal harmonic oscillator. So here the solution will be of this kind: a cos omega t and plus a phase factor. So this is our charge. So in that case charge will not dissipate, so there is no dissipation in the system. But ideally every component, every electrical circuit component, they have some finite resistance. So this inductor also have some finite resistance, and this capacitor also has some finite resistance. So practically there is no ideal LC circuit, so there must be some resistance. So for that we have an LCR circuit. So we have an inductor, a capacitor, and we have some resistance. So this is resistance, inductor and capacitor. So for that we have this, so for this circuit the equation that we have is this. So if we take a loop and apply Kirchhoff law, then we will get this equation: L di dt. So this is voltage drop across this inductor, and across this capacitor it will be Q by C, and across this resistance it will be IR. So this is our equation for a LCR circuit. Now we know that I equal to that current is the rate of change of charge. So I will be dq dt. So if we replace I here, then we will get L d2q dt square plus R into dq dt plus q by C equal to 0. So if we arrange the equation, so we have d2q dt square plus R by L dq dt plus 1 by LC into Q. So so first we have to look at the equation carefully, and let us see how what are the physical things that we can tell about the circuit. So we have this R by L dq dt plus 1 by LC into Q. So in this equation, so if we look at the, so you can tell a lot from dimension analysis. So if we look at the dimension of this, so what will be the dimension? So it will be Q into t to the power minus 2, because it has dimension of Q and it has t square. So it has dimension of Q t to the power minus 2, and this has dimension of q t inverse. So this r by l, from dimension analysis we can say that it must have dimension t inverse. So that means this r by l, it corresponds to time inverse, or this l by r, it is a time scale of the system. This is one time scale. So similarly, from this equation we can see that this q has the dimension of this. That means this 1 by lc, 1 by lc dimension must be equal to t to the power minus 2. So this it will be 1 by lc should be hmm, or so that means lc, root under lc, it is another time scale of the given equation. So we have here two time scale. So what are the two time scale? So if there is no resistance, then I mean for pure lc circuit, we have this term and this term. So in that case the only time scale present in the system is this. So this time scale corresponds to our oscillation time scale. And so this term, this corresponds to the damping. So as this corresponds to the damping, that means this r by l or l by r, it is our damping time scale. So as you can see, if r is 0, then this damping time scale is, so if we put r0 here, for r equal to tends to 0, this damping time scale tends to infinity. So what does this signify? That means there is no damping in the system, as we have seen in the case of LC circuit, that the solution, it is purely oscillatory. So it will oscillate for infinite time, and there will be no damping. But if there is resistance present in the circuit, then there is a time scale corresponding to the resistance value. So it will be a damping time scale. That means in this time scale the energy or the charge of our system, it will dissipate. So if we look at the energy, so if there is no damping, then our charge will oscillate like this with respect to time. So there will be no damping. So this is for purely lc circuit. So this is our time axis and this is our q axis. But if there is damping present on the system, then uh, we will have a solution of this kind. So it will, at after a finite time, then this charge will tends to 0. So this oscillation time scale, so these are basically oscillation time scale, and it is of the order of root under lc, oscillation time scale. So it is a root lc, and this corresponding to the damping time scale. So this damping time scale is l by r. So in that way we can get any so if we are given any equation, and if we are asked to show what are the time scale of the system, that we can easily get from this dimension analysis. So like you can do any equation, you can take any equation, and if we do the dimension analysis, then you will get the part which will correspond, which has the dimension of time. So that is time scale of the system. And and by looking carefully at the equation, you can clearly specify which time scale corresponding to which physical property. Like here, this 1 by lc or this lc, it correspond to the oscillation time scale, and this l by r, it corresponding to the our damping time scale. So this is how we can tell about the time scale of the system. And now suppose so the equation that we have for our damped harmonic oscillator we get is this: d2q dt square plus r by l dq dt plus 1 by lc into q. So this is our given equation. And if we want to do or solve this equation in Mathematica, or do calculations with that. So for that, first we have to non-dimensionalize the equation. So for that, we as we have discussed in one of our previous video. So how to non-dimensionalize equation? So q have here dimension of charge. So if we divide this with a charge value, so this is a constant value of charge. So now this unit, this is dimensionless, and we can write this as capital Q. So we can write Q as Q into Q0. So and in the similar manner, so here we have two variable, one is Q and one is T. So both so T, so we have to divide this with a value of time. So suppose tau is our one time scale of the system. So we are dividing t with tau, and that we are calling as t prime. Or for convenience, let us write down t bar. So this is our original time, and this t bar by t, that we can write down as t. So t bar, it will be equal to t into tau. So if we replace both this in our equation, then what we will get? Then we will get, here we will have q0 into q, and t will have t bar will have this plus r by l d of q0 q divided by t into tau plus 1 by lc into q0 into q. So what we are doing, uh, first we are identifying our dependent variable and independent variable. So this q has a dimension of charge. So that is why we are dividing this with a charge, with a constant charge value. And this t has dimension of time. That is why we are dividing this with a time scale of the system. And we are replacing this q and t bar with these equations. So if we replace that, then we will get this d2q dt square, and we have here, so q0 will be cancelled out from all the equations, and we have here tau squared plus r by l tau dq dt plus 1 by lc into q. So if we multiply with tau square, then we will get d2q dt square plus r tau by l into dq dt plus tau square by lc into q. So this tau is one time scale of the system. So we can, so what are the time scale that are present in the system? So one is this L by R, and one is root under LC. So we can assume any one of that. So let us take this L by R time scale. So if we if we assume tau to be L by R, and if we replace that in the equation, then the equation that we are left with will be d2q dt square plus r by l into tau, and we will replace tau with our damping time scale. So l by r dq dt plus 1 by lc into l by tau square. So it will be l by r squared into q. So if we simplify this, so d2q dt, what we are left with, plus dq dt plus l by r square c into q. So now if we look carefully, this q this is a dimensionless quantity, this t, this is a dimensionless quantity, and if we look at this L by r square c, so this is also, this has also no dimension. So this is just a purely a number. So we can denote this. So denote this L by r square c with a number, suppose gamma. So this is a purely number, because this L by r square c, it has no dimension. So the equation that we are left with is a pure equation, and there is no dimensions involved. This q and this t, they are all dimensionless, and we can write down this as d2q dt square plus dq dt plus gamma q. So these are just variables, so we can rename them, and let us replace this q with y, and t just so q with x and t with t. So if we do that, the equation that we so finally we are left with d2x dt square plus dx dt plus gamma x. So this is our equation of LCR circuit, where this gamma, so this is L by r square c, and after that, if we solve this equation, then we will get x as a function of time. So this x and t, they are dimensionless. So from this value, so from this form, if we want to go back to our original form, how we will do that? So now we have to do the reverse way. We have replaced x from q, so q will be function of as a time, and what we have for dimension analysis, for what we have this q by q0 is capital Q, so we have to replace that. So capital Q, we can replace that as q by q0, and this t is t bar divided by tau. So tau is our damping time scale, and that damping time scale is L by R. Let me check. Yeah. So L by R. L by R. So this will be the solution. This is how we can go back to original solution once we get our uh, solution from this non-dimensionalized equation. So the process is the following way. So first, you have your equation. You identify your independent variable, dependent variable, and after that you use this kind of transformation, the time scale involved and this charge scale involved in the system, to non-dimensionalize this. So ultimately you will get a non-dimensionalized equation with numbers, and we can solve this with the help of Mathematica. And if we solve this, then in the reverse way, we can get our original quantity that are involved in the problem. So we can get the charge as a function of time. So this is how we proceed for a given equation system. So let us analyze this equation in Mathematica. This d2x dx plus gamma x. Yeah. So the equation that we have is this: d2q dt square plus dq dt plus gamma q. Now suppose we want to know the solution of the equation. So suppose we assume the solution of this kind: a cosine of beta t plus phi into, so since there is damping in the system, so there will be exponential decay, and so suppose it has of this kind, e to the power minus alpha t. So suppose this is our solution of the equation. So what are the unknown here? So this a, b, alpha and phi, they are not known. So how to solve this equation? So we can calculate its first order derivative and plug in here. We can calculate its second order derivative and plug in here in the equation, and we will get a equation. So let us do that first. So this is our how the functional form of our solution look like. So a this is our functional form, and so first what we have to do, we have to evaluate the first order derivative. So let us do that. So this is so this command, this derivative command, it will calculate the first order derivative of this function with respect to t. So if we do that, so this is our first order derivative, and similarly we can calculate its second order derivative also. So for that we have to specify here the order of derivative. So if we specify 1 here, it will calculate first order derivative. As you can see from both these two values are same. And if we specify 2 here, it will calculate its second order derivative. So this is second order derivative. Now what is our given equation? So this is our equation: second order derivative plus first order derivative plus gamma into qt. And we want to solve this. This command, it will give us the equation first. So let us check. So if we write down this, so this is our equation that we want to solve. So for solving, we have to write down the solve command, and we want to solve for what? So we want to solve for this alpha and beta. So if we execute this, so this is the solution of alpha and beta. So this is really complicated look like. So the idea of solving this kind of equation. So this is our equation that we get. So if we look here, so this is our equation, and what we can do here, so we can collect the coefficients of cosine and collect the coefficients of sine. Because if we have a solution of this, if we have an equation of this kind, suppose a into sine omega t plus b into cosine of omega t. If we have a equation of this kind, then since this sine and cosine, they are orthogonal, that must means that the coefficient of sine, like coefficient, so coefficient of sine and coefficient of cosine, they should be 0. So we have to have these solutions to be 0, and from the equation that we are having, from that we see that this cosine has some coefficient and there are sine, they have some coefficient term. So these coefficients, they must be equal to 0. So for that we have to write down this command. So let us denote the equations first. So this is our equation, and from that equation we want to collect the coefficient of this cosine term. So we have to write down this command. So let us just ignore for a moment. So this is our equation, and from the equation we want to collect the coefficient corresponding to this cosine beta t plus phi. So if we run that, it will give us the coefficient of cosine, and we can see that this exponential term is present in everywhere. So we can divide this uh, with this. So a exponential minus alpha t. So if we divide with a e to the power minus alpha t, then it will be our cosine coefficient. So let us denote this as cos coefficient, and similarly we can get our sine coefficient also. So for that we have to write down here sine function. So we want to now collect the coefficient of sine. So this is, let us denote this by sine. So once we collect the coefficients, now what we want to do? We want to get the solution when both the coefficients are 0. So the coefficient of cosine is 0 and the coefficient of sine is 0. So we have to solve equations when this cosine both are simultaneously 0 for alpha and beta. So we want to get solutions of alpha and beta when these coefficients are 0. So you have, for that we have to write down this command. So I'm just copy pasting it. Okay, just this. Yeah. So these are the set of solution. So you can see that this is one set of solution for which this both the coefficient will be 0. This will be another set. So there are four set of solution. So this beta equal to 0. If we have beta to be 0, then we can see that uh, from the equation that we have, if we put here beta equal to 0, then we have q equal to a cosine of phi into e to the power minus alpha t. And since phi is a constant, so this is now a new constant, and we can write this as b e to the power minus alpha t. So there is no oscillation present in the system if beta is 0. So q will be purely decreasing. So this is the case of over damping. When we have this beta term to be 0, there is no oscillation present in the system, and the system will die down immediately, the system response. So this is an over damped case. So we are interested in under damping. That means the system will decay down the solution, but there will be some oscillation. So it will decay with some oscillation. So that the case we are interested in. So we are interested for non-zero value of beta. So we can work with any of the first two coefficients. So if we write down, so here, so set, so it will show us the first set of solution, and if we write down here 3, it will see us show us the third set of solution. So we are interested with any of the first two. So let us, you can see in the following comment. So and we want to extract we want to replace the value of alpha and beta in q that we have assumed first. So for that we have to write down this comment. So this is the value of alpha and beta which we want to feed in this Q. So this alpha and beta we want to feed in this set. So for that we have to write down this replacement command, and if we run this, then this is the how the Q look like for this set of alpha and beta. So this is our equation, the how the charge look like. So now the system, so since this is a second order differential equation, so it will have two initial conditions. So what we have done till now, so till now we have this equation d2q dt square plus dq dt plus gamma into q, and from that we have obtained a solution of q to be a e to the power minus alpha t cosine of beta t plus phi, and the values of alpha and beta that we have replaced with our one of the case for underdamped oscillation. Now there are these two variables which we don't know. So this is a second order equation. To know the value of these two variables, we have to know two initial conditions. So that means so we can know the charge as at initial time. So let us say this is 1, and we have to know the derivative of this charge or the current at initial time. So let us assume to be 0. So if we know these two, then from that we can calculate this a and phi. So let us see how to do that in mathematical. So for that we have to write down this command. So first let me copy, and then I will explain. Yeah. So what it will do, it will solve two sets of equation. And what are these? So one is this this function, or this function evaluated at time 0, which is equal to 1. So this is our one initial condition, and this is our second initial condition. So what it is doing here? So we are calculating the derivative of this function with respect to t, and we are replacing t at t. We are replacing t with 0. So this portion, this is just evaluating the derivative of this function at time t equal to 0. And what is the value of that? The value of that is 0. So these are the two equations that we want to simultaneously solve, and we from solving them we want to get a and phi as a function of this alpha and beta. So if we do that, then we will get the set of solutions. So these are set of solutions which we can which are which you can obtain from the value of gamma. So let us work with any one of that. So now again in this here we will replace this a and phi with any of the sets. If we look carefully, then this solution 2, it has four solutions. So what will be our first solution? So this is our first solution. If we write down 2 here, so this is our second pair of solution. If we write down 3 here, this is our third pair of solution. And if we write down 4 here, so these are fourth pair of solution. So we can work with any one of that. Uh, we are replacing here this a e to the power minus t by 2. So this a and phi we are replacing with this set of solution. So if we do that, then the solution that we are getting is this. So this is the solution of our given equation. So if we want to see how it's look like, so let us plot this. So first do that. So for plotting, we have to write down this following command. So plot solution of gamma t, t 1 to 10. If we do that, yeah, yeah. So gamma value we have to replace. So yeah, here we can replace gamma. So gamma, and if we execute this now, so this is how the solution look like for the gamma value 2. Now we can change the value of gamma. So we can manipulate the value of gamma, and we can see how the solution look like. So for that we have to write down the manipulate command. And what we are manipulating, we are manipulating here the value of gamma. So we have to specify the range of gamma over which range we want to manipulate. So gamma, and suppose we want to manipulate it from 0.3 to 10. So if we is taking time, yeah. So you can see that for this gamma value, uh, for gamma value 0.03, we are having this kind of oscillation. And if we increase our gamma factor, then we can see that how the solution changes. So you can play around with this any kind of equation, and you can play with how the solution look like with different sets of parameter. Like by varying one parameter, you can look how the solution, how the plot or the function changes. So these are some basic use of this derivative and integration function, and solving this differential equation. So this is one way of solving this differential equation by using inbuilt function. So there are other ways. The standard way by which we solve any differential equation. So today I will briefly talk about Euler method. So what is Euler method? So suppose we are given with a differential equation, first order differential equation of this kind, this general first order differential equation. So and we want to integrate this. So basically we if we want to find x as a function of time, so this will be another other function. If we want to get x as a function of time, that means we have to integrate this function, or we have to evaluate the area under the curve. So what we can do, so to numerically calculate this, what we can do is so we know our integration time limit. So suppose we want to integrate this function from time ti to tf. So suppose this is our initial time and this is our final time, and within this time scale, within this time limit, we want to integrate this. So first we have to discretize this time in some step. So uniform step. So suppose this is ti and this is tf. So suppose we are discretizing it. So we will evaluate this function at every point here. So we will evaluate function at all these points. So and how so suppose this is our nth point, and this is our n plus 1th point. So what does Euler method tells us? Euler method tells us that x at n plus 1, it will be equal to x at n plus h into function of x n t n. So what is h here? H is this time difference. So since this all are uniform, so this is our h value, and like h is the difference between two time data point. So this h we can write. So if there are n number of data point, then this h will be tf minus ti divided by n. So if there are n data points, then it will be n minus 1. So this is our the difference between these two time data series. So this is our h, and we are evaluating the function at xn at this point, nth point. And what will be tn plus 1? So this will be tn plus h. So basically h is the difference between 2 points, so that is why n plus 1 will be equal to tn plus h. So this is the update rule. So the idea is that so the gist, what is the gist? So we have this equation dx dt equal to f of xt, then x at n plus 1 at t n plus 1, or we can write down this in this way: x at t n plus 1 will be equal to x at t n plus h f at x n t n, and t n plus 1 it will be t n plus h. So let us look at one example first. So suppose we have this equation dx dt equal to minus 2x. So for that, what will be the Euler update rule? So here Euler update rule will be x n plus 1 equal to x n plus h. To what is the function? The function is minus 2x. So this x we have to evaluate at this point. So it will be minus 2 into xn. So it will be 1 minus 2h into xn, and tn plus 1 it will be tn plus h. So this is our update equation. So how we can get so from this, how we can get x as a function of time? So what we can do here, we can use for loop. So for the length of n, so this is our t initial, this is our t final, and we are discretizing it in. So suppose we have taken here n equal to 100 intervals, and each interval we will compute the xn and tn by the with the help of our previous known value. So initial value will be known to us, and from the initial value we will get this first value, and from this one we will get this value, and in the following way, if we execute go and do this, so we will get all the points here. So this at every point we if with the help of this update rule, we will have our series of x, and we will have our series of t, and we can do a list plot of that. So if we do the list plot, then we can see how this x changes. So this, there will be discrete points. So since this is list plot, so there will be discrete point. So this is, suppose this is our first point, this is second point, third point, and we can in this way we can see how this function changes. Now is this equation so the major problem of this Euler method is the convergence of the function. So what may happen? So the accuracy of your result, so that depends on how small you are taking your h value. So if we have this equation is equal to minus 2x suppose, and we have x at t equal to 0 is 1, then the solution will be to the power minus 2t. And if we plot this, then we will get this exponential kind of fall. Now, if we do this with the help of Euler method, so we will get some discrete with the help of Euler update rule. So suppose we get this data point set, and if we join them, so suppose we get this curve. So this is for some value of h. Now, if we increase the value of h, so suppose this curve we get from h equal to 0.01. Now if we increase h equal to 0.1, then the behavior of this solution it may change. So suppose for h equal to 0.1 we can have solution of this kind. So there is a problem of convergence of our given. So this is our real solution, how the real solution look like, and this is how the solution look like if we solve this with the help of Euler algorithm. So the accuracy of the Euler algorithm, it it heavily depends on what is the value of h, or what is the time step size that we are taking. So for higher accuracy we have to take smaller time scale, and if we take smaller time scale, then there will be large number of data set within the time interval, and you will need more computational computational time taken will be more. So there has to be do some kind of balancing or optimization on what should be the optimum value of age we should take, because if we take age value to be very low, then the time it will take, it will be very large. But if we take age value to be very if we take age value not very small, then there may be some problem of convergence. Like it, the graph that you are getting, it may not converge with the original graph. So that is why there need to be a optimum value of age we need to take. So how to let us now look at equation and see how to solve this with the help of Euler method. So let me first write, just copy paste the code, and I will explain. So suppose we have we have a function that f of xt, like dxdt equal to minus 2x, that we are discussing right now. So this is our given function, and we want to solve this in the, suppose we want to integrate this in the time interval from 0 to 5. So let us take from 0 to 5 seconds. We want to see how x changes. So let first we are taking 1,000 data points here, or thousand intervals, time interval. So we are breaking this 5 second interval into 1,000 points. And so that is how we are defining our age, that the final value minus initial value divided by number of steps that we want to take. And since this is a first order differential equation, that means we need to specify one initial condition. So suppose this is our initial condition, that means x at t equal to 0 is this. And we need one array. So what we need and why we need an array? We need an array because we need to store this number. So for suppose here we are calculating this x n plus 1 and t n plus 1. But after solving this, we need to store them, because if we don't store them, then when you want to do the list plot, so there will be no information of the how the solution, how x what is the value of x at this time. So that is why we need to first compute these two equation for every time step, and after evaluating this, we need to store them in an array. So that is why we are defining an empty array here. So this is our empty array, and in the empty array, so first we will feed the initial condition. So how to feed a number in an array? So we can do that with the help of append command. So let us first look at this command append. So suppose we are defining an array. So this is our empty array. So this is our empty array. Now if we append here, so append, so we are appending in the array. So array. So suppose we append 1. So you can see that this 1 is appended here. Now if we write down 2 here, so first 1 is appended, now this is appended. Now suppose you want to store another number. Suppose you want to store 3, so you have to write down just 3. So you can see that the previous ones are already there, they are not erased, and the number that you are updating, it is updating in the next to the previous value. So we can, if we now execute this, so 5 will be stored after 3. So you can see that, yeah. So this is the use of append command. We can append any number to an array. So that is why in the array, first we are appending our initial condition. That means what is our initial time and what is our initial displacement, that we are appending here. So if we execute this, so you can see that this is our function, this is our initial function, yeah. So this initial time 0 and initial displacement 1, that has been appended to the our given array. Now we want to run a for loop here, because we want to execute the value of this function, the value of this f of t function at each time interval. So for every 1000 data point, for every 1000 point, we want to execute uh, these two equations, and then we want to append them. So for in for loop, we have to write down four argument. The first argument is the initialization. So this is our initial condition, and the second argument is the checking condition, like for how long the for loop should run. So where should it stop? So you have to specify the end point. And the third one is increment. So how you want to increment the value of so this is our increment condition. So in the for loop, what you will do? So first it will take n value to be 1, then it will increment n with 1. So in the next run, the n value will be 2, and it will check that if it is less than nf. So if n value is for 2, it is less than 1000, so it will run the loop, and in the manner, when the n value will be 1001, then it will be no longer be less than nf, and it will break from the code. So these are the three arguments, and the fourth argument that we have to give is the body of our loop. And that means what you want to do in the loop. So generally this all the four arguments, they are separated by commas, and within one argument you can write down multiple command with this semicolon. So this is our first argument. So this is our initialization condition. This is our checking condition where to stop the loop. This is our incremental condition, and this is our body. So in the body, what do you have to do? So we have to write down this Euler algorithm, that x at n plus 1 equal to xn plus h into this function evaluated at this. So we are writing down this. So it will take the initial value first. So these two values it will take, and it will so these two lines, these are evaluating the Euler algorithm. And after that, once we evaluate this, we have to store these two numbers in our array. So this is our array, and we have to store these two. So for that, we have to write down. So this is for storing this, and once we store this, we have to for the next run, we have to update these two values, this x initial and t initial. It has to be updated with the current value, because for the next run, we will use that value. So let me clarify this with here. So suppose this is Tn, this is n plus 1 point and n plus 2 point. So when we are evaluating Euler algorithm here, what we will write? We will write x at n plus 1 equal to x n into h f of Tn xn, and Tn plus 1, it will be Tn plus h. So after evaluating at this point, we have to evaluate at next point. So when we want to evaluate at this point, then we have to write down this equation, x n plus 2 equal to, it will be x n plus 1 plus h f t n plus 1 x n plus 1. So whenever we are calculating this x value and t value, we are using its value from its previous time. So that is why we need to update, uh, we need to update this, we need to write down these two update equation. That means the value that we get from the current loop, we are assigning it for our next run to the x initial value, and the value we get time, the value of time we get from our current loop, we are assigning it to t initial for our next run. So if we execute this, so we will get the data set of our uh, given equation, the solution of this. So let us execute this first. Let us write as ti, this is our t initial, it is not executing. So there is some problem. Yeah, I think it is running some slow. This is our NF. Yeah, you can see from here. So this is the same code. So if we execute this, so this is another function, that dxdt equal to minus xt, and this is our given initial condition, that x at t equal to 0 at 1. So what is the equation for this? So equation for this is the following, that dx dt equal to minus x into t, and our initial condition is this, at t equal to 0 is